Hello everyone, Philip Roper here, and as Angela said, I'm from the Freight and Heavy Vehicles group here at ARB, and I'm one of the engineers who handles a lot of vehicle simulation and testing work, and I'm here today to help you understand a little bit more about safe operation of especially long multi-combination vehicles in remote areas. So I'm going to go through a few of the technical aspects that are important to this type of vehicle operation. We'll be looking at how we measure safe performance, how we can design the safest vehicle for a particular task, minimising load height, which is one of these design aspects that is very important to improve stability, and also working out what speeds are safe for certain radius of curves. And I'm just waiting for my slides to come up. Okay. When we talk about measuring safe performance, I'm really talking about high speed stability because it is the key to safe operation. Low speed manoeuvrability is a practical issue for all multi-combination vehicles, and you need to consider it in the context of where a vehicle will operate and how it will interact with work sites. But a vehicle's high speed dynamic stability really equates to the safety of its on-road operation. A number of measures can be used to grade the safety performance of a vehicle, and those measures are influenced quite heavily by certain aspects of vehicle layout, which I'll try to cover briefly today. Resistance to loss of control and resistance to rollover are the main measures of safety, and the performance in those areas is quite heavily affected by the type of couplings that are used between trailers, the wheelbase of the prime mover and the lengths of the trailers. It's effectively their wheelbases as well. The order in which the trailers are assembled into the truck, and the height of the loads, or more importantly the height of the centre of gravity of the vehicle. And I'll go into more detail in that in a few slides' time. Now, at this point I'm going to go through 4 important measures of safety, and those are static rollover threshold, high speed transient off-tracking, rearward amplification, and load transfer ratio. All of these can be modelled using vehicle simulation prior to building a vehicle, and I'll talk a little bit about that. But first I just want to ask you if you recognise any of these measures. Now we're putting a poll on the screen. Angela, who spoke to you earlier, has just turned on the poll feature, and there'll be a question on the screen asking whether you are familiar with all of these, or some of them, or none of them. And if you can give me an indication of your knowledge in this area, that'll help me to work out how much detail to go into in the next few slides. So start answering the poll questions. I see some of you are already working on the poll question. 3/4 of you have already given me an opinion. That's good. And nearly everybody has answered the question. So in a few more seconds I will ask Angela to show the results on your screens. Okay, I believe you can now see the poll results on the screen, and yeah, fewer than 20% of you have heard of all of those terms. Nearly half of you have never seen these terms before, so that's fine. That means I can now give you a bit of information that will help you to understand the safety of multi-combination vehicles as they travel on the road. Thank you for voting in that. I'll now go to the next slide. Right, so the first one we want to talk about is static rollover threshold. This is one of the basics. Unlike a car, the truck is likely to roll over rather than skid when you go around a corner too fast. And static rollover threshold is a measure of how likely it is to do that. The measurement is a multiple of gravity, so it's a measure of lateral acceleration, which is acceleration in the sideways plane, measured in a number of G's. And the higher your static rollover threshold for a vehicle, the safer the vehicle is. The reason we use static rollover threshold as a measure of safety is that quite a long time ago, when some research was done on crash numbers or crash rates among certain types of vehicles, a strong link was found between static roll threshold and crash rates. In that small chart on the right-hand side of the screen, you can see a whole lot of crashes plotted. They're the dots for a range of vehicles. They're all 5-axle semi-trailer combinations in North America. Their crash rates are there and their static roll thresholds are plotted as well. So you can see towards the end where they have a static roll threshold of 0.7 Gs, the crash rates are down below 10, that represents less than 10% of the vehicles that were involved in rollover crashes. 0.7 Gs means that it takes 0.7 times the force of gravity acting sideways to roll a vehicle over. Now on my chart, which is the larger one, filling most of the screen, I've shown here at an SRT level of 0.3, we are at about 0.8 rollover accidents per million miles. But if we were to raise static rollover threshold to 0.35, we reduce that risk by 22% to less than 0.75 rollover crashes per million miles. If we go further, we can get a 1/3 reduction in risk just by going up to a static roll threshold of 0.4. To work out static roll threshold, we drive a vehicle along a tight radius path, a circular path, and increase the speed at a slow, steady rate until the point of rollover. Now that's how we determine static roll threshold doing a vehicle simulation. You can do it on a real road, as is alluded to in this picture here. But in real life, the definition of static roll threshold involves putting the vehicle on a tilt table and tilting it until you see that it's about to roll over, measuring how much acceleration it takes to do that. In the performance-based standards scheme that operates in Australia, which is one of very few schemes in the world that uses static roll threshold as a regulatory control, this SRT value has to be at least 0.35 Gs for general vehicles, and if you are moving passengers or dangerous goods, the SRT has to be at least 0.4 Gs. Non-PBS vehicles don't need to meet these requirements, and many of them don't, but the design and choice of a vehicle combination for any task really should take into account its rollover risk and try to minimise it. I mentioned before that load heights were an important design consideration, and I'll just illustrate how load heights apply to static roll threshold. The biggest single influence on static roll threshold is the height of the vehicle, or more correctly, the height of its centre of gravity. I've got a drawing here of a popular vehicle combination, which is a 4-axle truck and a 5-axle trailer. The two load spaces have identical centres of gravity, so the height of the load space is effectively the same, or the centre of the mass of the load space. Now the rigid truck has an overall lower centre of gravity than the trailer, and that's because of the weight of the chassis of the truck itself, which is higher than the trailer. And so that's why we have two different static roll threshold values here. SRT for RCU1 and for RCU2, they are different values. And you can see here that the trailer, being roll coupled unit 2, has a much lower static rollover threshold than the truck does. The roll coupled unit label, by the way, refers to sections of the vehicle that are connected to each other in a manner that transmits roll movement. The rigid truck is a single unit and has to roll as one object, and the trailer body is also another single unit that has to roll as one object, but the drawbar in between the truck and the trailer is fixed, doesn't transfer any roll energy between the two bodies. So the truck is able to roll over without the trailer rolling over, and vice versa. In a semi-trailer, by contrast, if I show you the previous slide, you can see here that as the trailer is rolling, and it's the trailer that is causing this roll, it is pulling the prime mover up with it, and that's because it has a coupling in the middle there called the fifth wheel coupling, which does transmit roll, and that means that the two of those have to roll as one unit. So what we've shown here is that we've got an SRT of only 0.34 Gs for this entire vehicle combination, because once the trailer has rolled, then obviously the whole truck has crashed. In the next slide, I'll show you what happens when we reduce the height of the load. We started off with the centre of gravity at 2.85 metres, and we got an SRT of 0.34 Gs. When we reduce our centre of gravity to 2.2 metres, which does require quite a substantial reduction in the total height, the centre of gravity goes right up to 0.45 Gs, and it's even more dramatic as we reduce the centre of gravity height even further. So reducing load height is the single biggest contribution you can make to improving static roll threshold performance. Suspension and tyre performance can affect the results too, but to a far lesser extent than load height. Even reducing the overall mass of the load is not as effective as lowering the height. You need a dramatic reduction in mass to produce appreciable reductions in SRT, but it can be done if you have to. Of course, lower load heights are not practical in all applications, and where possible it's advisable to use a longer load space if you can, so that you can spread the same load weight out across a larger area and then therefore occupy less height. That's fine for bulk materials, but it can't be done in all circumstances, and in those cases you just have to go for a substantial reduction in mass to try and improve SRT. But this principle does hold for all truck and trailer combinations. The lower you can get the centre of gravity for a vehicle unit, the better its rollover performance will be. So that's static roll threshold handled. We'll now move on to high-speed transient off-tracking, which is one of two measures that we can calculate by doing a simulation of a lane change manoeuvre. High-speed transient off-tracking is called HSTO, and I'll try and call it that from now on in the presentation. And it is a measure of the lateral distance that the last axle on the rearmost trailer of a truck tracks outside the path of the intended steering, or the steer path of the truck. And it's measured when we do an ISO single lane change, which is designed to simulate trying to avoid an obstacle that's on the road. So you can see here that if we move across by about 1.46 metres with our blue steer path, hopefully you can see my pointer there, the front steering wheels of the truck follow that blue path as intended, but the last axle of the whole vehicle follows the red path, and it shoots out further by a distance that is equal to the HSTO measure. And so here we've shown us 0.6 metres of overshoot by that last trailer axle. I can show you that in an animation here. The curved line is the steer path of the vehicle, and these four lines are stepped measurements of how far out the last trailer has moved. So I'll stop talking while I play this in case my audio is affected by the video. So you would have seen then that the trailer stepped out quite a distance, and I'll see if I can pause it at the right point. Right, so that trailer here, there has almost touched that first parallel line, and that means that it's got almost 0.6 metres of HSTO, and those lines represent 0.6 and then 0.8 and 1 metre and 1.2 metres, I believe, of swing out of the rear trailer. This HSTO measure is quite important for working out how well a vehicle is going to interact with other road users, really, and how much space it takes up on the road, how well controlled the trailers are when it does an evasive manoeuvre or even just tries to travel along in a straight line. High-speed transient off-tracking is affected by various aspects of vehicle geometry, and I'll discuss them a bit more later on. Now, another measure of vehicle tracking ability when doing a lane change manoeuvre is called Rearward Amplification, or RA. This is the ratio of lateral accelerations at the last trailer and at the steer axle. And shown in this diagram at the bottom half of the page here, you can see that we've put in a small lateral acceleration at the front of the truck using the steering wheels, and at the rear trailer the body has moved enough to create a much larger acceleration. And this is what you expect because there are articulation points in the vehicle. So every articulation point introduces the potential for movement to be amplified. So the degree of amplification of the lateral accelerations towards the rear of the truck is an indication of how out of control, if you like, the truck gets when sideways movement is introduced. Rearward amplification is calculated by just looking at those two acceleration figures. So if we have a 0.15 G input at the steer axle and a 0.3 G acceleration is measured at the trailer, we get an amplification ratio of 2. So our rearward amplification figure is 2. Now, rearward amplification in the PBS program in Australia, the performance-based standards, is compared with static rollover threshold, and the RA figure is not allowed to be any more than 5.7 times the SRT of the vehicle, or the SRT of the last trailer in the vehicle. So if we have an SRT value of 0.35 Gs on our final trailer, then the limit on our rearward amplification is 5.7 times 0.35, which is 1.995. So that vehicle I showed you with an RA figure of 2 is not safe enough for PBS approval. This is based around the fact that if you apply enough of an acceleration at the front, it's going to be amplified so much as it gets towards the rear that you are in quite a lot of danger in terms of getting to the point where the vehicle might reach a critical limit on lateral acceleration. The more resistant that trailer is to roll, in other words, the higher its SRT is, then the better off you'll be and the higher an amplification you can accept. Now, the final important marker that we want to look at is load transfer ratio and its relationship to safe speeds. We'll call it LTR, and this is a measure of how imbalanced a load is between the left and right wheels on the vehicle. It's related both to the SRT and to the speeds that the vehicle is travelling and the duration over which lateral accelerations are sustained. As a vehicle rolls to one side, the centre of gravity of the load moves sideways, and this causes the wheels on one side to carry more of the load than the wheels on the other side. Now note that this is not due to the load shifting in the load space. It's entirely due to the vehicle leaning to one side, so the centre of mass of the load tilts to one side and therefore moves closer to one set of wheels than the other. If half of the load from one side of the vehicle is transferred to the other side, the LTR is 0.5. And on this chart here, you can see this bold black line reaches 0.5 for some of the travel around a roundabout, which is what this illustrates. If all of the load from one side is transferred to the other side of the truck, so one set of wheels has no weight on it and the other set has all the weight, then you're up here with an LTR of 1. And when you get an LTR of 1, it means you've got no load on one side of the truck and it's about to fall over. The chart that I'm showing you here was generated in simulations of a vehicle travelling around a roundabout, and you can see on the bottommost line, when we're travelling at 35 kilometres an hour, the LTR rarely gets above what is considered a safe level of 0.6. It does touch it a couple of times, but not for long enough to really cause any trouble. And 0.6 is considered generally an indication of safe truck operation. When the speed was increased from 35 to 48 kilometres an hour on that same roundabout, we got wheel lift because the weight was completely removed from one side of the truck, and that meant that the truck was rolling over. Now, this truck was probably considered a safe enough vehicle to have on the road, but what was not realised by people operating it is that a small increase in speed, in this case 13 kilometres an hour difference, when travelling through a particular roundabout, put the truck at almost guaranteed risk of rolling over and crashing. Now, actually I'll just go back to that slide. So load transfer ratio is a very important indicator of vehicle safety and is closely linked with the type of route that the vehicle is travelling. And I'll come back later to talk about how to work out what speeds are safe for certain vehicles on certain curves. So now that we know all those 4 different markers of vehicle safety, we'll talk about how to put them together and how to maximise the safe operation of any vehicle design. The question that people need to ask themselves when ordering vehicles and determining what truck has to do a certain task is how do you know that your trailer manufacturer is designing the safest vehicle combination for the task? Obviously, logistical constraints can dictate the design of some vehicles. For example, there will be certain types of load that simply will not fit on all types of vehicle combinations. But where possible, the safety performance of various designs does need to be considered when deciding on the type of vehicle for a particular task. The types of couplings that are used, the length of the trailers, the order of those trailers, those things are all important to the 4 key safety indicators that I was talking about earlier. All of those measures can be improved with one or more of these 4 dot points here. Fewer articulation points make the vehicle easier to control. Using turntables and fifth wheel couplings which provide a roll transfer between trailer units instead of pin couplings, that can improve performance as well. Minimising the overhang distance of a coupling behind the wheels on the trailer that it's mounted to, that will improve performance, as well as in lengthening drawbar dollies. Lengthening trailer wheelbases and then improving suspensions and using stiffer tyres and the right pressures, that will all help as well. And you might be thinking to yourself, some of these things are not practical, and that's true. If you increase trailer wheelbases and drawbar lengths, while you're improving the high-speed safety of a vehicle, you'll also be making it more difficult to turn it through certain intersections and to fit it around the entrances and exits of certain loading yards. Those, of course, do need to be considered, and if you build a truck that doesn't fit, then it's not going to be any use to anyone. I mentioned coupling types back here, and it might be useful to just illustrate that for some people. This drawing here shows a junction between 2 trailers in a typical road train, and that usually involves a pin coupling at the back of one trailer with a dolly connected to it, and then a fifth wheel coupling on the top of the dolly, which holds the next trailer in the chain. So a pin coupling looks like this bottom left photo here, and a fifth wheel is like the top right photo over here. The pin coupling is similar to what you would use on a car with a caravan or normal trailer, and it doesn't transmit any roll energy through it. So the trailer is able to roll without the towing vehicle rolling. A fifth wheel coupling like this, though, clamps the trailer coupling very firmly and ensures that roll is transferred through the coupling, and that means that if a trailer has a tendency to roll, then it can't roll very far without also pulling the prime mover or the previous trailer with it. And that certainly helps stability and aids with the high-speed manoeuvrability or high-speed safety of the vehicle. Here in the bottom right diagram is an example of how a B double or B triple trailer set is constructed. Instead of having a tow bar at the back of a trailer with a dolly connected to it, you put a fifth wheel coupling on the rear of the first trailer and then connect the second trailer directly to it. And that creates a flexible but rigid as far as roll is concerned vehicle combination. This drawing shows where those different coupling types can be employed to move the same type of freight. The colourful trucks in the top 2 pictures here have A and B couplings. Now I should go back and mention also an A coupling is a pin coupling. We just call it an A coupling because it's the first type of coupling that that has been discussed and that generally is known as an A coupling across the world. A B coupling is the type that you have here on top of a dolly, or in a B double combination. It's the type that transmits roll. So A coupling, B coupling. When you put a B coupling in a chain and then have an A coupling and another A coupling, we refer to that as a BAA combination. So in this case we've shown 2 quad road train vehicles, and they have exactly the same trailers in them, but the first one puts the B double set at the front and the second one puts the B double set at the rear. The turning performance is probably similar between these 2 vehicle combinations, and a lot of the safety indicators will also be the same. But with putting that B combination at the rear and having a B coupling as the last coupling in the chain, we reduce rearward amplification. So that can make a vehicle much more stable if it had to do an evasive manoeuvre, or if it was just simply negotiating curves. The rear trailer set is going to amplify any lateral acceleration is a lot less than the rear trailer set in the BAA combination. Now, a further enhancement that you can do when playing with couplings and designs is to locate toe couplings as close to the wheels of the preceding trailer as possible. And in the third diagram on this page, I've shown you what I mean by that. Instead of these dollies connecting to pin couplings at the back of these trailers, they have these long goosenecks which reach up and over to reach the centre of the axle group of the preceding trailer. That means that any lateral accelerations that are imparted on those couplings by the trailers are going to be minimised, because that centre axle group is going to move sideways a lot less than the back of the trailer does, and that means that this dolly ends up with a lot less lateral acceleration than otherwise might be the case with a standard A coupling. In the vehicle that I've shown there, it was practical for these particular operators because they were transporting a very dense bulk product, so it was quite easy to shorten the length of the bins, or to build a truck so that bins of that size would be practical. This would not work if you were carrying containers perhaps, or certain other types of bulk material, but it could be done in this case, and it resulted in a vehicle that was very easy to drive in comparison with a standard A triple. And that's an example of how you can move couplings around and use slightly different types of couplings to maximise safety. As well as those basic elements of vehicle design, you can also take certain safety features and apply them to just about any vehicle. There have been a lot of developments in recent years, and a range of helpful safety features are now either standard features or available as optional on a lot of new trucks. They provide varying levels of improvement on the drivability and comfort and fatigue resistance of vehicles. They act in both active and passive safety performance. And I've done listed a handful of them here. Probably one of the most important recent developments, and the most dramatic, has been stability control and rollover protection systems. These are electronic systems which rely on the measurement of acceleration and roll and yaw in prime mover and trailer units, and computerised braking systems can react to the movement of vehicles and stop a truck from rolling over in some circumstances. And they've provided a very big increase in safety and made it possible to bring some vehicle combinations under control that previously would not really have been an ideal vehicle for some drivers to look at, and they would have been quite unpopular. Improved visibility is another thing. LED lights and reflective markings, bigger mirrors are becoming more commonplace. Comfort is improving quite a lot for truck drivers, and this in turn reduces fatigue, makes the operation of heavy vehicles much safer than it used to be. I haven't gone into many of those safety features because the list of them would go on for pages and pages, but there is quite a lot that can be done, and it is easy to retrofit it into older combinations if you are replacing prime movers more often than replacing trailers. And now going to the final stage of this presentation, which is about safe curve speed analysis. And this is an area in which we try and take an existing vehicle which may or may not have certain design and safety features that I've mentioned before, but we can look at its performance and work out how fast it can go on certain sections of road to maintain a safe level of operation. Any vehicle has inherent limits on how quickly it can negotiate bends of certain radii, and we're not talking about trying to go faster with trucks. We're just talking about whether or not travelling at or below the legal speed limit might actually be dangerous for some vehicles, and this needs to be analysed, especially when trucks run a certain route every single day with different drivers in them. People are not familiar with the loads, and accidents can happen as a result. Depending on the type of the load and the vehicle design and the terrain, vehicles travelling the same route regularly, such as in a mine hauling operation, may encounter curves that need to be negotiated at a much lower speed than the rest of the route. So the process of determining safe curve speeds usually involves a bit of on-road testing to characterise the dynamics of a certain vehicle and to learn how it responds to certain steering inputs and how it responds to the curves that it travels along. And then computer simulation can come into play and then put that same vehicle virtually through a range of different curves and speeds, and through that to work out a map of safe curve speeds for that vehicle along a certain route. Here's an example of what might come out of such an analysis. This shows that those curves that are in the range of 120 to 130 metres radius for a certain vehicle, speeds of no more than about 50 or 55 kilometres an hour were found to be safe. But on a much larger curve along the same route, 70 kilometres an hour was a safe enough speed for that vehicle. So if the speed limit along this road was 80, or if that, in fact using multi-combination road trains, it's usual that the only speed achievable will be about 80 to 85, depending on load, then it was quite likely that eventually a driver was going to come along not familiar with the route entirely, perhaps not familiar with how the trucks behave, and just try travelling at 60 kilometres an hour perhaps through some of those tight curves, and a calamity would probably result. And so this kind of safe speed analysis can help operators to preempt such problems and work out a safe operating regime for an entire route. So, summing up what we've talked about in the last half hour, high-speed dynamics are very important for vehicle safety, while low-speed manoeuvrability is obviously a practical consideration. It's important to be able to maximise the safety performance of a truck at high speed. The main indicators of safe performance can be simulated and designed into a vehicle. There are a lot of new safety features that can also help out and try and improve vehicles that for some reason couldn't be designed to be as safe as possible. The arrangement of a load, and in particular the height of a load, has a large effect on safe operation, and safe speeds can be calculated for specific vehicles along entire routes to try and maximise safety. Now I've come to the end of my presentation slides, and I'd like to thank you all for your attention, and we've got about 25 minutes left now if anybody wants to ask any questions. So feel free to start typing in the question box over on the right, and I'll do my best to answer them. And the first one has come through. Someone has said, can you please adjust the projector so we can see all the contents on our screens? Have any of you had trouble seeing any of these slides? Because they should be all showing up on any size screen. If there has been any problem, don't worry, because you will be able to view a recording of this later if you need to, or we'll be able to give you a PDF of all of the slides. Okay, so anyone who has any technical questions about any aspects of this presentation, you're most welcome to either ask them now, or you can email us the questions later on, especially once you have received the PDF of the slides or the link to the PDF. I'm happy to respond to any queries later on and give you some advice on any of those issues that we've been talking about today. There was quite a lot of technical content there, and I made it as brief as I could, but I still had to include quite a lot of information, so it may have been a bit much to absorb in just half an hour. Now, there's a question from Rob Smedley at TMR. Thank you, Rob. Rob wants to know if I can go into a bit more detail as to how the values for rearward amplification were determined. So I'll give that a go. I'll go back to the slide where I was talking about rearward amplification. Now, this diagram of rearward amplification here starts with the measurement or the deliberate input of a certain amount of sideways acceleration down here at the steering axles. And that's represented in this simple drawing by a graph with a fairly small amplitude. And at the back of the vehicle, we are measuring the lateral acceleration that occurs as a result of the input at the front. And so we're measuring what looks like approximately twice as much lateral acceleration at the rear. So we might have had 0.15 Gs going in at the front, which might correspond to a small steering input, or actually probably a fairly severe swerve around an object on the road. And when that has happened, as the lateral acceleration has propagated through the vehicle from the front to the back, we've identified twice as much, at 0.3 Gs lateral acceleration at the back. And so we work out rearward amplification from that by dividing the larger figure by the smaller one. So 0.3 divided by 0.15 gives us 2, or an RA figure of 2. And that means that when you put an acceleration in at the front, you're going to get twice as large an acceleration at the back.
It's Anthony Jumanchev here.
Welcome, Anthony Jumanchev.
Thanks, Phil. I might just add to that as well, just trying to read between the lines there, knowing what I'm being asked with that question about rearward amplification. And the question was, can you go into more details about how the values were determined? So we've explained how they're calculated, but originally determining the safe levels for RA, what makes a vehicle pass or fail this standard. Good point. That was done a long time ago based on an analysis or a snapshot of the vehicle fleet at the time, and we were trying, the work done by ARB at the time was trying to capture the top 40% of vehicles. So they set a threshold of 5.7 times, and that's what the slide at the moment is showing you. So if your rollover threshold is 0.35, you times that by 5.7 times to get a number of 1.995. So you can see the RA result of 2 is not safe enough for PBS approval. So that 5.7 number was determined based on 40% of the best performing vehicles of the Australian vehicle fleet at the time, which was about 1995, I believe, coinciding with that number of 1.995. Coincidental sake. So I hope that helps. And there's a few more questions there as well. Maybe I'll hand that one to Phil to answer. Yes. I think that question about the Austroads road design guide is in reference to the safe speed analysis for curves, and I think the work that we do in terms of providing a safe speed analysis is for mining companies, often operating on their own roads, and about the safe operation of their vehicles. So they're not really designing roads at this point. They've got the roads, they're stuck with them, and they're just trying to operate their vehicles as safely as possible on those roads. It's instructions that they will give the driver, or some kind of restriction that they'll place on the operation of those vehicles to make sure that they're within the safe speeds for each curve.
And to the extent that a safe curve and a speed analysis would apply to normal suburban roundabouts and intersections, that's really where we're trying to fit certain vehicles into the existing road network, isn't it? Because we already build all of our intersections so that they geometrically will accommodate any vehicle that they are likely to see that's going to be allowed to use them. But you get certain types of freight, such as concrete in a concrete agitator, which are much more dangerous to carry in terms of how they behave with regard to rollover risk. And that was the reason that one of those analyses was done, I believe, to work out how safe or how fast you could drive concrete agitators through a certain roundabout without rolling them over. So if that's what you meant by the question about this presentation and it's linked to the Austroads design guide templates, then that's what we mean. Here's an interesting question from Les Bruiser. LTR is not currently part of the PBS requirements, and he wants to know if in our PBS assessments that we do at ARB, do we consider LTR as an additional performance measure to make a judgment about the performance of vehicle combinations? Would you like to answer that, Anthony?
Yes, I will. We do not consider LTR as far as it's not in the PBS rules. But if we're doing so we just check the vehicle against the rules that exist, and unfortunately, I would say unfortunately, that LTR was not included because it's a very insightful standard, and it gives you probably more information than just passing or fail. You get to understand how close it is to passing. And load LTR, for those that It's another term. Phil explained 4 terms for measuring vehicle performance. LTR is another one, and it's load transfer ratio. You did explain it?
Yeah.
Sorry, I must have been daydreaming at that point. I'm sure you weren't daydreaming. LTR, load transfer ratio. So we use that for doing a study of a particular vehicle if they want to improve their operation, understand the limits of their vehicle. It's not done part of the performance-based standards scheme as such, but it's very useful for helping people understand vehicle safety.
It could certainly be included, but the only high-speed manoeuvre that we do in the performance-based standards at the moment, as far as that involves any steering, is the lane change manoeuvre, which I illustrated towards the start of this presentation. And if we measure the LTR in that, it would be quite high. And I would say that we would have to try and come up with perhaps a manoeuvre that involves going through a normal intersection or a roundabout at normal road speeds and check LTR at those speeds if we're going to put it into PBS. It certainly is worth considering, and I think it would be good to put it there. I think we might have come to the end of the questions now, Anthony. Would you agree?
No more are coming through.
No more are coming through, yes. All right, well, thank you, everyone, for watching this presentation, and I'll just advance to the last slide, which shows you where you can go for a bit more information. My name and phone number and email address are up there on the screen at the moment. If you would like any further information or answers to any other questions that pop into your head as soon as I've turned this thing off, you are most welcome to make contact, and Anthony and I will both do our best to help you. So until next time, when we come up with another topic, thank you for attending. Bye-bye.